Hello everyone. Today we're going to talk about continuous integration and continuous delivery on AWS on an example of a base Java project. What we're going to cover: lots of cool technologies, AWS, Kubernetes, Ansible, Gradle, lots of modern DevOps practices of how to make it all work together in a way convenient to a developer. How to stand up an integrated project from scratch and establish the CI/CD workflow. On the way, I'm going to show you solutions to many common problems. Let me briefly describe the project, and then we'll dive deep into individual topics to show how it's done. First, to demonstrate CI/CD, we need to have a business app to build, test, and deploy. To make it closer to the real world, I've chosen to write 3 small interacting apps. That illustrates better the typical interactions and the typical required infrastructure. Let's take a look at this lucid chart diagram. The first app is called simply API. It proxies calls to a public XKCD APIs and returns a description of a comic from xkcd.com website. The starts reporting app collects information about the user API calls. The stats API makes those stats available to the user. We utilize a message bus for loose coupling between the API, which should serve customer requests quickly, and the stats reporting apps. The stats reporting app writes information into the database, while the stats API reads from the database and returns that information back to the user. Code for the project lives in this GitHub repository under Roman Aster user. Project name is base Gradle-CI/CD. We utilize Git version control system as an industry standard, and the production ready version lives in master branch. Each feature gets its own branch of master, and then a pull request, PR, is created to merge that branch with the feature implemented back into master. We must implement a process to ensure that the code master is ready to serve customers in production. The common name for the process is CI/CD. There are 2 common ways to trigger vetting of code: when a pull request is created and when code is merged to master. Checking the PR helps us understand if the feature is fully operational and if it's breaking anything. But we need to check that everything merged together also works and to produce a set of the so-called artifacts which can be deployed to production. Thus, we really need both trigger types. What should happen as a part of this code vetting? First, for Java project, we need to compile and build code, turning it into Java bytecode executable on a virtual machine. Then we would run unit tests to ensure the smallest units of the applications, called classes, work correctly. Next, we build deployable artifacts. It can be executable jars or WAR files containing an application and the bundled dependencies, or it can be a Docker image which also includes the Java virtual machine. After building the artifacts, we should deploy them. If the deployment goes smoothly, the behavior of the deployed applications can be extensively vetted with integration, performance, and load tests. All of these tests check functionality of the application, but the perf tests, in addition, check how quickly individual requests can be executed, while load tests simulate realistic environments, typically with multiple concurrent requests. If all the builds, deployments, and tests were successful, then we need to signal that all tests pass. For the PR builds, that would unblock merging code to master. For the CI master builds, the successful build would trigger creation of artifacts, Docker images, releasable to production. If the PR build fails, then the code in that branch needs to be fixed first. You could see one of the Status checks indicates a failure, and well, I cannot really merge the code. I can override it as an administrator, but no, it doesn't really let me merge it. But if the CI build failed, then no production reusable artifacts are created, and these master builds have to be fixed first before one can release something or before one can base any of the feature work off of master. Till now, we assumed that infrastructure components with which and through which the applications interact already exist. Container deployment clusters, databases, messaging buses, etc. But they don't just magically appear. One has to provision them. One can create the infrastructure components manually. Say, find a server for the database, then install and configure MariaDB. Such an approach has multiple issues. First, it's not really reproducible. A small variation of server setup or DB configuration may lead to substantially different outcomes or even a complete failure to install. Second, one still needs to get servers from somewhere and manage them. Well, these problems are solved with an infrastructure as code principle. We script the provisioning of servers, installation of the databases, messaging buses, container management tools. It's a little hard to buy physical servers with a script. Well, the virtual servers from cloud platforms such as AWS, Google Cloud, Microsoft Azure come to rescue. It's possible to provision servers from them programmatically. We've converged that there should be a script to provision infrastructure components. Where would this script live? The script is code, and the place for code is the GitHub repository. It's the easiest to put the infrastructure scripts into the same repo as the application code and make it follow the same PR and CI flows as the application code. Then, the same PR can contain the necessary changes for the entire feature, both the infrastructure components and the application components. For example, if we want to change from Postgres to MariaDB database, then we change the infrastructure script to provision a different DB flavor, but also change the application code to use a different driver. I mentioned the need for a cloud platform to fully exercise the IAC principle. I chose the Amazon Web Services, or AWS for short, for this simple project as the most popular cloud platform. It's a common choice for home projects, startups, as well as big companies like Netflix, LinkedIn, and Facebook. AWS has a great variety of options for each type of infrastructure component. For example, AWS Relational Database Service provides 6 flavors of relational database. A messaging bus can be established on AWS with SQS, Kinesis, Managed Kafka, Amazon MQ. Containers can be deployed in AWS in a variety of ways. ECS, Fargate, EKS, or even Elastic Beanstalk. We utilized MariaDB, Amazon MQ, and EKS combination, which I will show later. Note that for many managed services, you only need to specify how big of a compute server you want, but you don't actually manage the server directly. Amazon does it for you. AWS has its own options for orchestrating the execution of CI/CD workflows: CodeBuild, CodePipeline, CodeDeploy, and CodeStar. The barrier for using AWS is really low. For this sample project, I've paid for all compute and storage resources out of my own pocket and didn't burn a hole in it. It was about $20 a month maximum. AWS has a free tier components and the ability to create and destroy the infrastructure dynamically, which I have actively utilized and will show you later. Lastly, if your company has to comply with security standards and laws like GDPR, AWS is a real lifesaver because it provides out-of-the-box switches, for example, to encrypt databases at rest and to enable TLS on a load balancer. So you'll spend much less effort satisfying your information security officers. In sum, in my experience, using AWS translates into great savings of time and money. This concludes the general overview of the technologies and methods to establish a modern CI/CD workflow. Now, it's time to dive deep into the topics and show how it's done. Let's talk about the build. Two major build tools for Java projects are Maven and Gradle. In the previous video, I've shown Maven in action. Now it's time to showcase Gradle. Gradle is the build automation tool optimized for faster builds. You might not feel the difference for small projects, but when you cross, say, 20,000 lines of code, you'll start being painfully aware how slow your builds became. And it's a bit of a hassle to switch the build tool at that time. Gradle incremental build capability and the task cache allow skipping what didn't change between the builds. Moreover, with a distributed Gradle cache, one can leverage builds on all machines in your fleet of build agents. I'll show the distributed cache in action later in this video. Let's open IntelliJ and look at the project. The Gradle project is organized into several modules. Three modules correspond to the applications: API, Stats API, and Stats Reporting. There is also a shared module called Data Model. What does it have? It has the format of data exchanged by the applications. There are two schools of thoughts on separation of apps into repositories. Option 1, have a separate repo per application. Or option 2, put all apps into the same repo. A multiple repos approach is often cited as the alternative to a monolithic application living in one repo. But no, a single repo approach, also called a monorepo, is perfectly legitimate. After all, Google adopted it. The monorepo approach makes it easier to ensure the set of applications can work together. True, it's always a danger that the apps in a monorepo will start depending too tightly on each other, with a common module containing half of all code. That's an anti-pattern, and the dev team should be careful adding things to a common module. As you could see, common module in our case is very, very tiny. The other monorepo concern, the build duration, is exactly what Gradle solves. If a certain independent module did not change, then Gradle will spend about 1 second on it to get the build result from cache. There is another shared module in the project, however. It's called the Flyway. Flyway module traces the database schema, including all of the changes. Since it lives in the same repo, can trace all schema changes, then it provides a convenient way to introduce those changes alongside changes to the application code. There is a separate module for the performance tests. Those are written with Gatling. And if we were to have integration tests in this project, we'll put in a separate module as well. You guys should have integration tests. Gradle build files can be written in either Groovy, which is an old style, or Kotlin DSL, which is a new style. I've tried Kotlin DSL for this project, but have mixed feelings about it. It's nice to write build files the same way which you would write the code in. It has autocomplete, syntax highlighting. However, it's harder to write build scripts in Kotlin, and not all plugins are fully compatible with it. It worked at the end with extensive Googling and with some trial and error, but well, I'm not sure if I would recommend it. The choices of dependencies and the code tools are the same as in the previous project: Spring Boot, Lombok, which is now part of IntelliJ, as well as Google style checks, which have the definition file in here on the config folder, then enforcement of 100% code coverage with unit tests, and then Docker images being built with a Jib plugin. You can check out another video for how to do it in Maven, and it gives more details as well. I've mentioned the distributed cache for Gradle. So how does one enable that? Let's look at the settings gradle.kts file. It has a build section, specifically to configure the remote HTTP cache. Well, it's always actually enabled, but the cache URL does not always exist. So even in this case, if cache URL is not defined, the build will successfully run. It's just going to be slightly slower. That will rely on your local cache. Let's talk in more detail about infrastructure as code. For this project, I used AWS to programmatically provision infrastructure. AWS CloudFormation service is employed to define all infrastructure components declaratively with YAML scripts. Then we can execute the scripts to stand up the needed components. What do we do for multiple infrastructure components? Just like when writing Java code, we split the infrastructure ecosystem into pieces and write small cohesive scripts per piece. Then we compose the full ecosystem out of these pieces to facilitate clarity and reuse. CloudFormation can be used from AWS command line interface or CLI without any extra tools, but it's not the easiest way to use it. We need some sort of a glue to stick the pieces together. Use the output of one script and another script and set the environmental variables as needed, plus perform tasks not managed by CloudFormation. Ansible is an excellent glue which can do all of that. It supports both the declarative code style of how certain components should look like and the imperative code style, for example, when we pass variables and managing conditional logic. Ansible playbooks encapsulate complete tasks, for example, standing up an infrastructure ecosystem for an environment. Let's take a look. In our application, we have app deployment YAML playbook. It's composed of the roles, and roles are cohesive. For example, we have a role called message bus, which stands up the message bus, and have a role called RDS DB, which stands up the RDS database. We can further split playbooks by the layer of the component we deal with. For example, the networking layer can be separated from the database layer, which is different from the app deployment layer. Then the layers, which are changed very infrequently, won't need to be executed alongside, for example, the application layer. However, this brings the danger of the networking layer only ever getting executed once, and then any changes deemed too dangerous to be automatically managed. For this project, I chose to include all layers in a single playbook. For example, we would create the virtual private cloud first, then create the subnets, and then we provision resources such as the cluster to deploy containers into and pass those subnets ID in there. Switching between different infrastructure and application deployments in prod would then be done via changes to domain name service DNS routing. It's a tough choice in real life about whether to divide into layers or not. It does depend on how much the dev team really wants to manage, or if you have other teams in a company which manage very low-level infrastructure. So we chose to use Ansible, and how do we execute that? For learning purposes, experiments, and the POCs, we can execute Ansible from the command line on the developer machine. And here's the sample command: Ansible playbook dash the inventory name and then the actual playbook to execute. However, we need some other place to run the CI/CD workflows. This brings us to the build infrastructure. Build infrastructure is a common place where CI/CD workflows are executed. It provides transparency of what's building now, the build history, visibility into who broke the build, the medium to collaborate on any fixes and improvements, plus the ability to test production deployments in lower environments. We adopted infrastructure as code approach for the application infrastructure. It would be great to adopt IAC for the build infrastructure as well. We should provision it in AWS too. There are two kinds of options for the build infrastructure in AWS: third-party build tools and native build tools. Jenkins is the most widely adopted third-party build tool in 2020. It provides great user interface, flexible customizations, folders for different build types, and great visibility. It's possible to automate deployment of vanilla Jenkins. However, the power of Jenkins is in its plugins, which are often applied and configured manually. Before you know it, the Jenkins server turns into a pet instance, which is very painful to redeploy. The alternative is the AWS native build tools, such as CodeBuild, CodePipeline, and CodeDeploy. These native AWS tools adopt native AWS access control through Identity Access Management, or IAM for short. They don't require maintenance of any servers. The build infrastructure for those services can be provisioned with CloudFormation and Ansible, which we are already using. It's appealing to utilize AWS native build tools, isn't it? Well, they have their cons. CodeBuild and CodePipeline are more of a bare bones interface without the richness of Jenkins. For example, you don't get out of the box build locking on the resources for concurrency management with CodeBuild. And there is no folder structure in CodeBuild or CodePipeline, so it's a bit overwhelming to have more than 10 different build definitions. You can see here that we are approaching 10 build definitions, and that's for one project. So if we were to have 3 or 4 projects, it's going to be a long list, maybe of multiple pages. Only recently, CodeBuild closed a big gap and introduced native test results reporting. They can be found under report groups. If you click on one of the groups, we could see that there were 2 reports executed recently. And down there is report history, which shows the results of individual tests with the test case and the actual class for which they were executed. We could see that this particular set of test cases passed. All of them passed. For this project, I demonstrate native build tools, but the choice is yours whether to use Jenkins or native build tools. Maybe in a couple of years, CodeBuild and CodePipeline will grow a little bigger, more convenient, and will become as convenient as Jenkins. We've talked about various types of infrastructure defined as code. Let's switch back to IntelliJ. So where would that infrastructure live? So we already mentioned that we should bundle infrastructure code alongside the application code, so it is in the same repository. And here we chose to put all infrastructure into the operations folder. However, we separate between the application infrastructure in the apps subfolder and the build infrastructure into the CI/CD subfolder. There are some common reusable pieces between those 2 infrastructure types or different playbooks, which make it into the common folder. There's another folder called inventories, which define individual environments into which the applications are deployed. So typically, the definition of an inventory would have some static servers. However, in our case, it's only the AWS account, region, environment name, and versions of the components. We do not actually have the static servers which we would manage with Ansible. It's all done through AWS. Let's talk in more detail about AWS native build tools. CodeBuild represents a single build with the input parameters and the output, which can include build artifacts and the test results. If multiple types of activities are performed within a PR or CI workflows, then a single CodeBuild build is simply not enough. Instead, it's better to have a pipeline with many stages. Stages can include several actions executed in parallel or sequentially. Here, let's take a look at the PR code pipeline. We have a source stage, a build stage, and a deploy stage. And there are some actions in each of the stages which are executed in parallel, which I will touch in a bit. Naturally, we would want one pipeline for PR builds and one pipeline for CI builds, which is exactly what we have here. However, there is a problem. CodePipeline cannot be triggered from a pull request, where we attempt to merge an arbitrary branch to master. Only CodeBuild can do that. The easiest workaround I found is to have a CodeBuild trigger build which uploads code from a PR branch into a versioned S3 bucket. Let's take a look. The two bottom builds are the trigger builds, which check out the code from GitHub and upload code into the S3 bucket. Then a code pipeline is triggered by an upload of that zipped source code into the S3 bucket. Here's the S3 source action. Luckily, with this approach, we can create two pipelines which are very similar. One for PR builds and one for CI builds. An important question is where to store the produced Docker images. One can store them in Docker Hub or in AWS in an Elastic Container repository. The previous project utilized Docker Hub, but since then, Docker has introduced more restrictions on their free account, like rate limiting for the image pools, which pushes users towards paid accounts. And if I want to give my money to somebody, I would rather give that to Amazon. Hence, I chose ECR for this project. Here you could see that we have a bunch of private repositories. For each of the PR builds, a new version is uploaded in here into the repos, but when the CI build is successful, then the successful artifacts are promoted into the ones which can be released to production. They have the prod- prefix. There is another service which I mentioned in the beginning, and that is the code deploy. I have experimented with code deploy, but didn't find its use convincing enough. One would use code deploy to deploy raw CloudFormation templates, but this project has CloudFormation templates wrapped in a layer of Ansible, which makes a good case for simply using CodeBuild for deployment. A potential use for code deploy is the blue-green deployments, but they are out of scope for this video. You may still be confused about why we have so many CodeBuild builds. Well, here under the CodeBuild tab, all of the CodeBuild stages of the code pipelines are listed. So only those bottom two are pure CodeBuild builds. The other ones are parts of the code pipeline. The main outcome of a PR build is the decision on whether we can integrate the branch into master or not. One way to do it is to manually check the status of the PR pipeline, but wouldn't that be easier for GitHub to learn the build status and indicate whether code is ready to be merged? GitHub status checks provide such a way. CodeBuild triggered by a PR and the code pipeline triggered on a merge to master provide their status to GitHub automatically after the user follows simple setup steps. And this is one of such statuses. It's a PR trigger on a successful Gradle CI/CD build trigger PR build. However, our builds are triggered by an upload of source code to an S3 bucket, thus we need to do more work to report the final status back to GitHub. That is what GitHub status checks are for. GitHub provides extensive APIs and step-by-step guides on status checks. Here, this is the type of a call we need to make to the GitHub APIs with a token authentication. It's the post call based on the hash of the commit with the body, which includes the target URL. Target URL is what is linked here on the details word. Then clicking onto the details word can provide us a lot of useful information. It's whatever we want to link it to. For example, here for the unit test status, which we create by ourselves, we have linked it to the test reports, and we see that indeed that set of tests passed in under 8 seconds with 100% pass rate. But if there are test failures, then those will be indicated here, and the failures will be here at the top. Then it's going to be very easy to debug. As you could see, those status checks were required on GitHub. How it works is that you run the build with status checks first, then they appear on GitHub, and then you can go into settings and make them required. Here, these are the steps under the GitHub docs of how to make it all work together. So how did we actually implement that? There are calls to GitHub APIs from the code pipeline from under a particular actions. And those are the build status and the deploy status actions, which run in parallel with the actions which actually do the work, which do the build and the deploy. Those status actions wait for the main parts of the work to be completed, then read whether they were successful or not, and report the corresponding status back to GitHub. As you can see, one can report more than one status per build, which is why we made a call to GitHub API instead of relying on any of the regular processing which automated integration with AWS provides. Thus, everything is automated. A developer pushes a branch out and initiates a pull request. The PR triggers the CodeBuild trigger build, which checks out source from this repo and gets it to this bucket. Then the code pipeline is triggered from this bucket, which does all the work, and as the pipeline progresses, the statuses and links which help to troubleshoot are sent to GitHub. If the builds are green, which is this one, then we could merge code to master. But if the builds are not green, then that merge will be blocked. I've mentioned that we build Docker containers and that we deploy them somehow in AWS. Let's talk about it in more detail. There are several ways to deploy this container in AWS. Elastic Beanstalk, Elastic Container Service, ECS, with its spin-off Fargate, Elastic Kubernetes Service, EKS, with managed Kubernetes control plane, OpenShift Service on AWS, known as ROSA, as well as custom solutions to run containers on EC2 instances with the help of Docker daemon. Elastic Beanstalk has minimum configuration and integration options, not very flexible. ECS is a great option with just enough functionality, though it is slightly more expensive and is specific to AWS. EKS is a great option without vendor lock-in, while ROSA is a full enterprise option, which was released very recently and is in preview as of end of 2020. We would not consider custom solutions since plenty of standard options are available. So it's really between ECS and EKS. I played with both and ended up choosing EKS for this project to showcase the option of Kubernetes on AWS, and it worked great. EKS ensures no vendor lock-in, has faster deployments, and great debugging options. A common pain point for Kubernetes is the management of the control plane. Well, it's not at all a problem for EKS, since Amazon takes care of the control plane for its managed service. And what's left to the user is the simple deployment or scaling commands. Well, not quite true. One does need to deal with auth, but there are standard steps provided by AWS on how to do that. Let's talk more about EKS. We create an EKS cluster in a chosen AWS region across two availability zones. We configure a control plane, provision worker nodes, which are just EC2 instances. We could see that we have the cluster provisioned. We have two standard worker nodes, which are of T3A small size. For considerations of security, those nodes should be placed in a private subnet, which does not anyhow influence our ability to troubleshoot or debug problems. Note that many tutorials end up placing worker nodes in public subnets. We are lucky to use Ansible already. So we just hook up all Kubernetes operations through K8s Ansible module. So here's the Ansible playbook, and we use K8s Ansible module with the regular Kubernetes deployment files. So we use config maps and secrets to pass variables. We use AWS CLI and kubectl executables to connect to the cluster, check and troubleshoot deployments, see the logs. Some Kubernetes operations do lead to the creation of the resources in AWS, such as load balancers and security groups. Let me show you how to use kubectl command line to do some very basic operations. My AWS account was the one which is used to create the EKS cluster, so I can easily connect to it at this point. First, I need to set the namespace, which is non-default, so that's a standard gotcha here. Then I could check my deployment, and you could see that there are 2 pods available to serve traffic of each of our 3 applications. We could actually look at the pods. You would see that if there are some problems like invalid image name, then we would already be able to see that very easily, and we'll be able to debug that in no time with the describe command. Kubectl describe pod name. We see that, oops, something is missing, and something was the version, so I did not specify the version, and the job failed. So as you can see, for the flyway, we use the job type of the Kubernetes object. So let us look more at the pods. We could, for example, get logs for individual pod. Here we see that it successfully started. But if it was not, we would be able to see what's going on. And we could even log into the pod. So here we're under the pod, we can write the commands and really see what's going on if there are any problems. All right. Let me exit from the pod. As a usual word of caution, for deployments to production, one should consider creating an entirely new EKS cluster each time instead of doing upgrades in place. That has a lower risk of bringing your production down. A warm cluster in another region would provide a reasonable disaster recovery strategy for a critical application. Let us now talk about cost reduction. We've mentioned many AWS services used for application infrastructure, build infrastructure, and deployment orchestration. How much is it going to cost us to provision it all? Not much, after all. My maximum monthly AWS bill was $20. Here's what I did. The most expensive infrastructure component was the EKS control plane and 2 T3 small worker nodes. That would have been $100 per month if it was to run 24/7. However, we do not need the CI/CD environments to always be up. What I have implemented is bringing the application infrastructure up whenever the first PR is triggered for the day and shutting that infrastructure down automatically at 3 a.m. UTC. Well, it's a great reminder to go and get some sleep. It's around 11 p.m. in summer in the Eastern time zone. The automatic shutdown is triggered via the AWS Lambda function. Lambda function is created with CloudFormation. Here is the definition of this Lambda function. What it does is that it triggers the deletion of the stacks which have the EKS cluster, various databases, and message buses. It is sufficient to trigger at once the deletion of all of the stacks, such as here I pass the parameter to delete stack 1, stack 2, stack 3, and also clean up the resources in a VPC, which are created within EKS cluster. On the first round of deletion, we delete only the stacks which do not have the upstream dependencies, but the EKS cluster deletion fails because we need to delete all of the things which are built on top of the EKS cluster. However, if we kick off that Lambda function second time, then we can progress and delete the next layer of CloudFormation stacks. It appears sufficient to kick off the deletion for 1 hour every 5 minutes. And if the stack is already deleting, then it won't do anything. But if the dependent stack is deleted, then, well, we could proceed on deletion of another layer of stacks. We could have deleted the resources from the EKS cluster with the kubectl command, which I've just shown. However, it's more cumbersome to package the kubectl into AWS Lambda, and we would suddenly have one more artifact to manage. So just a short Python definition is plenty. Luckily for me, the build infrastructure is cheap enough to exist 24/7, which is really good since we can preserve the build history. I did exceed the CodeBuild free tier of 100 minutes per month, but the total cost ended up around $2. Finally, let me show you, as promised, the distributed Gradle cache. The steps to enable it can be found on gradle.org. In essence, you deploy an image, Gradle-build cache node, and then a version, and wire that with some HTTP URL, for example with a load balancer, and use that in your application. An Ansible playbook creates a distributed cache while the newly generated HTTP URL is used later by the builds. So we need to find a way to propagate that information from the playbook to the build. We use AWS Systems Manager Parameter Store for this purpose. The last step of the playbook is to upload the cache node URL into the parameter store. So here it is. Then what we do within the builds is we use that value from the parameter store to define an environmental variable, and then the Gradle build is able to use that. An elastic file system, EFS, is wired through EKS to provide a permanent storage of build cache. The build with a distributed cache is noticeably faster. A CodeBuild build takes about 3 minutes 20 seconds without a distributed cache, about 2 minutes 50 seconds with the distributed cache on the second and subsequent builds for about 15% savings. Well, the percentage savings should further grow with the project size, so it would be even more important to use the build cache. So technically, one can achieve comparable results with the local build cache, but then one needs to be careful to not access the local build cache concurrently. So if you want to have builds which run in parallel for CI and PR workflows, then they need to have separate build cache, or if you end up running multiple PR builds, those need to have their own instances of the build cache, and well, at that scale, you would end up benefiting from the actual distributed cache. This concludes our content for today. Let me summarize this feature-rich project. The project exemplifies best practices of coding, testing, infrastructure as code, DevOps, security, cloud provisioning, and cost savings. A modern, sustainable path towards continuous integration and continuous delivery was demonstrated on a working example. This project utilizes AWS, CloudFormation, and Ansible for infrastructure as code, and managed Kubernetes as a container orchestration system. Native AWS build tools, CodeBuild, CodePipeline, and ECR enabled build infrastructure. Our PR and CI workflows were uniform and consistent of multiple stages. The workflows are fully integrated with GitHub, with each stage independently delivering its status. A total of 16 AWS services were explicitly used. Multiple items were discussed in the video, but many more were omitted for the sake of time. Feel free to explore the code offer your suggestions as PRs, and use the code in your own projects. The code comes with a rather non-restrictive MIT license. Thank you for your attention.